Hi, my name is Michael Wang, and I'm a fourth-year PhD student in the Edge Lab at Princeton University. Today I'd like to talk a little bit about time-sensitive clouds, jobs with deadlines, an ongoing research project done in collaboration with Applied Communication Sciences. The main goal of this project is to achieve optimal deadline-aware resource allocation for jobs and data flows across a network of independent clients and computing clusters in the cloud. There are many variations on this general problem, but the one we focus on today is the task of transferring a file from a source to a destination over a network while trying to optimize for the completion time of the job and some network cost metric. Major challenges of this project include the heterogeneity of jobs, as well as the problem of selecting the best source to obtain data, assuming identical and perfectly replicated clusters, and the best path for that data to be sent across. Specifically, jobs may have a variety of time-dependent utilities, priorities, resource requirements, deadlines, and deadline types. In the figure on the right are some examples of jobs with variable deadline types, which we have characterized as sensitivities to deadlines: time-critical, time-sensitive, and time-insensitive. Currently, we only focus on single resource requirements, but it is not inconceivable that this can be extended to multi-resource constrained optimization at some point in the future. We focus on two subproblems within this project: the challenge of optimizing job performance in an independent network, and optimizing job performance and network metrics in the case where the network can be controlled. In the case of an independent network, the resource allocation problem has no control over the network itself. For example, in the case of sending flows over the internet where the user has basically no control over the routing and background traffic that already exists on the selected path. In this case, we formulate the problem as a distributed optimization where clients and clusters perform a handshake to determine which computing cluster to obtain data from. First, clients submit details of their job requests to our ITACT algorithm located on each cluster, which performs an optimization to solve for the Nash bargaining solution. The ITACT algorithm outputs both a congestion price, which is a measure of the load on the cluster, and an estimated completion time for the data transfer to the client. Then, based on these values, clients may choose the best cluster for the file transfer to both minimize load on the system and minimize the total time required for completion. The second case we address is the case of file transfer across a network, but this time the network is indeed controllable. For example, think of a circuit-switched optical network, where users are able to request the reservation of resources for a job. In this case, the problem becomes a joint optimization. Not only do users have to perform cluster selection, but also need to choose the path required from source to destination. What makes this interesting is that the network traversal time, T-network, depends on the bandwidth of the path chosen. A larger T-network incurs a smaller cost on the network. However, this results in less time for T processing, the time it takes for the job to be processed at the cluster itself, which may end up incurring a higher load on those clusters and can potentially make the job infeasible to run on that given cluster. This makes for an interesting trade-off between the joint optimization problem of cluster and path selection in a controlled network. If you have any questions, please feel free to contact me at mw7@princeton.edu. Thank you for your time.